Hello, everybody. I'm Dr. Benevides da Costa. I'm currently a principal researcher at the Technology Innovation Institute in Abu Dhabi, United Arab Emirates. I would like to thank the organized committee to have invited me to deliver this talk. It's a really pleasure for me to be part of the conference. My presentation, its title is a SIC-Free approach for rate-split multiple access systems. And this is a joint work with some research collaborators. So a special thanks to all these names who helped me to develop all the results and for the numerous insightful discussions that we had. Okay, so this is the outline of my presentation. Firstly, I will introduce some of the key concepts related to the discussions. In particular, I will discuss about massive MIMO, multiple input, multiple output. I will present some of the fundamentals related to this technology. And then I will describe very briefly the functionality of rate split multiple access. And finally, I will motivate the use of the polarization domain as an additional degree of freedom to be explored for the next generation wireless systems. So after this first part, then I will present the proposed approach, which aims to eliminate the successive interface cancellation process inherent to a rate split multiple access. So the idea is to rely on the polarization domain, exploring the polarization multiplexing to completely eliminate successive interface cancellation. Then I will show some simulations and comparisons with other baseline schemes. And finally, I will conclude my presentation by highlighting some of the key points and discussing some future works. Okay, so we start this part by describing some few words on massive MIMO systems, which can be defined as a communication systems with multiple users on one side, and a base station employ a massive number of antennas on the other side. So the key feature of massive MIMO is that this large number of antennas enables the base station to communicate with multiple users in parallel, simultaneously, using the same time and frequency. And this property leads to impressive performance gains when compared to the single antenna case, such as low latency, high spectral efficiency, high connectivity, and so on. And such appeal advantages have made massive MIMO one of the key technologies of 5G and beyond. And then as expected, it will continue to play a central role on beyond 5G. However, we have an issue related to massive MIMO, which is the installation of tens of hundreds of antenna elements in a tight physical space can create a strong correlation among the antennas. And this can put hard constraints on the physical size of practical antenna arrays and hampering the performance of massive MIMO. Because we have a limited physical dimension, and if you are going to deploy a huge number of antennas, sometimes the antenna space will not be enough to guarantee the incoming signals are independent. So one question that comes is how to mitigate this limitation? So the answer will be provided in the next slides, but you anticipate that we can rely on the polarization domain to equip more antennas at the base station and consequently rely on the advantage promised by massive MIMO on a limited physical space, consider a limited physical space. Multiple access schemes are also essential for the whole 5G system, as they can further boost the performance again of massive MIMO. In particular, late splitting multiple access, which is the main topic of this talk, it appeared recently in our community, research scientific community, and it appeared as a robust downlink multiple access technique for MIMO systems, which can deliver high spectral and energy efficiencies, optimal degree of freedom, robustness to imperfect channel state information. And thanks to these features, rate splitting multiple access can outperform all conventional techniques, for example, SDMA, NOMA, and OMA. So the main idea behind rate splitting is to partially decode interference and partially treat interference as noise. So this is different from SDMA, which fully consider interference as noise, and NOMA, which fully decode interference. So rate splitting multiple access can be seen as a flexible interference management scheme. Okay, but how it works? Actually, at the base station, considering the downlink scenario, at the base station, rate splitting multiple access will divide each user message in two parts. The first part of each message is encoded in a common symbol, which is intended to all users. And the second part of each message is encoded into private symbols. Each one is intended to a particular user. Then the common symbol and the private symbol are linearly precoded in the power domain and transmitted to the multiple users through the base station antennas. So the users will receive a superposition of the common and private data streams, in the sense that the common streams is detected first by treating the private message as interference, and next, the successive interference cancellation is executed to subtract the common message and recover the intended private streams. So despite the advantage of this strategy, there are some limitations. One of the issues is that due to the successive interference cancellation protocol, the data rate of the common streams will be always limited by interference. Another problem is that due to hardware limitations, imperfect channel state information, and other issues, the SIC process can be executed imperfectly, causing consequently residual decoding errors. And this reference demonstrates that these negative points, it can severely degrade the spectral efficiency of rate splitting multiple access. So it comes the question, how can we overcome the issue of successive interference cancellation? So the answer to this question and to the previous question about the limited physical space of massive MIMO, so the answer can be found in the polarization domain. Actually, dual polarized antennas arrays are a standard commercial system, so it's already commercialized in 5G, and it can be seen as an efficient way to deploy large number of antennas in limited physical space. In particular, compared to the single polarized antenna array, a dual polarized antenna array can build an array with twice the number of antennas, considering the same physical dimension. In addition to the spatial efficiency, antennas organized with orthogonal polarization, in this case vertical polarization and horizontal polarization, these antennas exhibit a low correlation, and this implies that the polarization domain offers an extra degree of freedom for generating multiplexing and diversity gains. So this presentation will take advantage of this additional degree of freedom, which means we will explore the polarization domain, and we will present a novel dual polarized rate splitting approach, which completely eliminates successive interference cancellation during the process. Okay, so how it works, how the proposed approach will work. So the basic idea is to multiplex the common and the private streams in the polarization domain instead of the power domain, which was inherent to the original rate splitting multiple access. Specifically, if you consider a base station and the users equipped with dual polarized antennas, the common and the private streams will be transmitted simultaneously in independent polarization. Here in the figure, we assign the common stream to the vertical polarization and the private streams to the horizontal polarization. This is for simplicity, but as I will comment in the future works, this polarization choice can be optimized. I mean, it can be designed in the sense that we're going to provide an optimal performance. But in this presentation, for simplicity, we assign the common stream to the vertically polarized antennas and the private streams to the horizontal polarized antennas. So based on this strategy, we will enable the users to recover the private and the common symbols directly from the assigned polarization. I mean, without the need to consider the successive interference cancellation. So in this way, all the SIC-related issues are avoided, and a user can recover their message with a lower computational complexity. However, we have a drawback related to this strategy, which is the users will experience cross-polar interference, which is caused by the depolarization phenomenon inherent to the propagation. So this cross-polar interference will affect the performance of the proposed approach. But as we will see, even subject with the cross-polar interference, the proposed strategy can outperform other baseline schemes without the cross-polar interference, but they rely on the successive interference cancellation. Okay, so to investigate and to illustrate the efficiency of the proposed strategy, we are going to consider a multi-group downlink scenario where one base station employ M2/2 pairs of dual polarized antennas, and each user employ dual polarized antenna, one pair of dual polarized antenna, and we have multiple groups of users. So the base station clusters the users into G groups, and these G groups are based on the likeness of their channel covariance matrix, which means that users within each group share a common covariance matrix. And we consider, for simplicity, U users per group. Okay, so how we to work the proposed strategy? Actually, we have a two-stage transmission approach. Basically, the first stage is to separate the users in groups. And after the users are separated in groups, then within each group, you employ rate splitting multiple access. Okay, so but first, how to separate the users in groups? So we have a disprecoder for group multiplexing. So basically, the main goal of a disprecoder is to avoid the intergroup interference, is to separate the users in groups. And then it is constructed based only on the channel covariance matrices. Then after this first phase, in the second stage, we will employ rate splitting multiple access to save the users within each group. And in that case, we need to design a precoder for the common symbol and a precoder for the private symbol. So the common symbol is broadcasted to all users, is intended to all users, and the private symbol is for each specific user will receive a specific message. its private message. So how to design these two precoders is another point, a key point of the proposed approach. And I will talk more about it, this design, in the next slides. But basically, we will just show that the common precoder can be designed as a random precoder or other precoders designed depending on the complexity you are expecting for behind the process. And the private precoder, it tends to avoid the intergroup interference. I mean, to cancel the interference coming from the users inside each group. And you have the power coefficient for the common symbol, the power coefficient for the private symbol. It can be fixed, they can be dynamic, and you have the common symbol and you have the private symbol. So basically, we need to design three precoders. One is the auto precoder for the group multiplexing, and two precoders for the second part, which is related to the common symbol, common message, and the private message. Okay, so the base station will transmit the signal. Here we can see the common message assigned to the vertical polarization and the private message assigned to the horizontal polarization. And the users, after the base station transmit this signal, the users will receive this signal where this is the full dual polarity channel matrix, and this is where we have the channel vector for the polarization I to polarization J. So the parameter chi, it means the parameter which measures the cross-pole interference. So when it's different from 0, it means that we have the cross-pole interference, okay? And you have the parameter zeta is the large scale coefficient, and n is the additive noise, okay, observed in each one of the polarization. Note that, as I mentioned, this polarization choice, it can be optimized, but in this presentation, it's considering this fixed polarization assignment. So this is an illustration of the transceiver design. So we see here at the base station side, the message are multiplexed in the polarization domain. Okay, so we have a polarization multiplexing for the private message, and each message, private and common, are transmitted in a specific polarization. And on the receiver side, the signals are recovered without the need to use successive interface cancellation. Okay, so in order to show the efficiency of the proposed approach, we are going to carry out some performance analysis, and you depart from this signal to interface plus noise rate expression for the common message and for the private message. I will skip in this presentation the details on how to attain, and also how to derive I mean, the intermediate steps on how to obtain the performance metrics. But I will try to briefly summarize how they can get it. So this is the expression for the common message, signal to interface plus noise rate. So the numerator, it means the desirable signal. The denominator is the undesirable signal. So you can see in the denominator, we have the noise, and you have the interference coming from the cross-polar interference, which is measured by the parameter chi. So we don't have any term related to the successive interface cancellation process, even because we don't have. So the idea is to design this common precoder and enable that this expression will be as high as possible. And this precoder, in this presentation, it is designed considered a random precoder with independent and identically distributed entries, following the standard complex Gaussian distribution. Of course, other different strategies could be proposed. For example, the matched filtered precoding, max mean fairness, among others. But for simplicity, we consider random precoder. And for the private message, we have this expression very similar. As I mentioned before, the whole for this precoder, private precoder, is to eliminate intergroup interference, which means is to ensure each private message reach only its intended user in the assigned polarization. Sorry. And in the denominator, we have similar terms. Basically, our signal is corrupted only by the cross-pole interference and the noise. So in order to derive some expression, it's important to first characterize statistically the channel gains. And the idea is to rely on some approximations. So if you consider the summand of each term of the sum is independent, is it possible to prove this denominator can be approximated by a gamma distribution? And the same here, in the same for the private message, but I will skip the details. Considering this approximation, the gamma distribution for the denominator and the numerator can also be considered as a gamma distribution, we can derive some closed form approximations for the outage probability. Actually, in this presentation, an outage probability means when either the common message or the private message are not be able to be decoded by the users, which means the target of the common message is below the threshold, or the target of the private message remain below a threshold. So this is a very simple expression. It's approximation, but as we show in the curves later, it provides it coincides with the simulation. And here we can see the parameter chi affecting our expression, which means when it's different from zero, it exists the cross-pole interference, which means that this outage probability will not converge when the signal to noise ratio the parameter rho tends to infinity. Some of will show also some expression for algorithm rate. Again, it's corrupted only by the parameter chi. So in its antenna in coarse form, and as they are very tight expression and very useful, especially if you assume you are investigating a complex system, which is composed by multiple groups, multiple users with multiple antennas. So achieving this approximation is very useful, at least to provide a first glance on how behave the proposed approach. So for the simulation setup, you will consider these parameters, which means the base station equipped with 100 transmit antennas. For the dual polarized, we consider M/2 collocated pairs, which means 50 collocated pairs of dual polarized antennas. And we simulated a scenario with 4 spatial groups, and each group contains 3 users. And the users employ 1 pair of dual polarized antennas. And we focus on the first group, where the users 1, 2, and 3 are located at the distance from the base station. And we consider also a fixed power allocation scheme with these coefficients. I mean, alpha is for the common message and beta for the private message. Okay, in this figure, we plotted the outage probability. So figure A is for different value of target rates, considering no cross-pole interference. And the right side is for different value of cross-pole interference. You can see a very good match between the analytical and the simulation, which corroborates the expressions. But more importantly, you can see when there is no cross-polar interference, the outage probability, it converts to 0 when the SNR goes to infinite. However, when the cross-polar interference exists, which means when it's different from 0, the outage probability does not converge. Why? Because in this case, when the parameter chi is different from 0, it means that the private precoders are not able to cancel the inter-use interference coming from the users of the same group. So this is the why the outage probability saturates to a given value. Okay, in this another figure, it's plotted the outage sum rate, and we compare the proposed approach with other baseline schemes. So the dual polarized MIMO rate splitting is the red curve, so it outperformed all the other schemes. Here, it means the successive interface cancellation when the error is 0. So even when you compare the dual polarized with the single polarized, rate splitting, multiple access, the dual polarized case outperformed the single polarized counterpart. But when you consider the NOMA, I mean dual polarized NOMA, rate splitting also outperformed dual polarized NOMA without successive interference cancellation error. Why? Because here rate splitting is a more robust scheme. And considering the proposed approach, we are providing some polarization multiplexing. We are recovering the message directly from the assigned polarization. So even when we have some cross-polar interference, we can surpass the performance of the other baseline schemes. So in the right side, this figure, we plot in terms of the SIC error, or as expected, the proposed approach, the curve is a constant because we don't have any, we do not implement successive interference cancellation in the proposed approach. But in the other schemes, when the error increases, the performance is drastically degraded. So this is the main advantage of the proposed scheme. It does not rely on successive interference cancellation. It fully eliminates successive interference cancellation. And finally, I showed some curves about Gort sum rate. And again, we have a perfect agreement between the analytical and the simulation results. And we compare the dual polarized MIMO rate splitting with the other baseline schemes. And in all the cases, our scheme can remarkably outperform all the others in terms of the sum rate. Okay, so this presentation, it shows a novel dual polarized rate splitting multiple axis strategy with the goal to eliminate successive interference cancellation by exploring the polarization domain. And our results reveal the performance superiority of the proposed scheme when compared to other baseline schemes. Okay, finally, I will conclude the presentation by mentioning some future works. One interesting direction is to extend the analysis, assuming the overlapping of different groups. In our analysis, we assume the outer precoder is able to fully eliminate the intergroup interference because we consider the users do not overlap. The group of users do not overlap with each other. But if you consider an overlap between groups, then we need to rely on a hierarchical rate splitting, which means that instead of transmitting a single common symbol, we can transmit a second common symbol. And the transmission of a second common symbol will help to mitigate the unconcealed intergroup interference. Another interesting direction is to extend the analysis assuming a more sophisticated power allocation strategy. We consider in this presentation a fixed power allocation strategy, so we can provide a formulation considering a dynamic power allocation strategy. Also, optimize the polarization choice. And for simplicity, we consider the common message is assigned to the vertical polarization and the private message to horizontal polarization, but this is not always the case in terms of performance gains. We can boost the performance if we are able to optimize the polarization choice. Another interesting direction is to incorporate intelligent reflective surface in the proposed setup in order to enhance the rate of the common message and to make it a more a robust scenario in terms of imperfect system interface cancellation, and also to deal with the cross-polar interference, because as I show, we have the signal is corrupted by the cross-polar interference, and if we use intelligent reflective surface, we are able to minimize the cross-polar interference because we are able to customize the wireless environment and reduce the cross-polar interference based on this new design provided by the intelligent reflective surface. Another interesting direction is to design data-driven models, especially because we are dealing with very complex system setup, which is composed by multiple groups, multiple users, multiple antennas. So sometimes the mathematical model and analysis become a little bit intractable. So designing data-driven approach will be of a great value to predict the performance. And finally, this is a more general direction. You can explore the polarization domain as a promising means to meet the high performance KPIs of SIC-Free, because we are able to deploy more antennas in a limited physical space. We can explore the polarization domain to guarantee a high security, improve the capacity, and so on. Okay, so thank you for the attention. So that's all I have on presentation. And any question, I'm open now for replying any question, but feel free to drop an email and I will be happy to interact with everybody. Thank you so much.